So today we will resume chapter 4. So in chapter 4, we have this process management. So our main topic of this chapter will be understanding what is a process, how process work. We'll study about the process management introduction. We'll talk about the process elements, example of process execution, process creation, termination, different state models of a process, mood switching, process switching, and then modes of process switching, and so on. Okay, so let's go one by one. So first of all, what is a process? Okay, a process is a program in execution. So in our computer, we have different programs. Okay, but whenever we are running a program, that program is called process. When we execute a program, then it's a process. Process execution must progress in a sequential fashion. So whenever you are actually running a program, there are some sequential steps that you actually need to follow. A process doesn't indicate a separate CPU. So whenever you're actually running a multiple program, that doesn't mean that you actually have a multiple operating system or multiple CPU. You have only one operating system and one CPU that is actually somehow handling multiple processes at the same time. Now, process management depends on that whenever you actually run the program, okay, we actually demand that program should be completed as early as possible, and at least the CPU should start execution of my program as early as possible. So whenever you close a program, okay, you want that instantly to close the program. Whenever you run a program, you want instantly to start the program. So basically, whenever we interact with a process or a program, we want it to respond to as soon as possible. So this is actually all of us want. We don't want to actually play a game where it takes a 5 seconds to respond. Just think, you are using Facebook, and every time you click a button, you have to wait 5 to 10 seconds so that the button actually responds. But what happens normally, whenever you click a button in your Facebook or in your computer, it instantly reacts to your command or to the demand. So we want the computer programs in a way that it will instantly respond to the user. So a process is a program in execution, and a process management is actually how we can manage, we can actually allocate resources so that the process actually responds to the user as early as possible. Okay, so this is the process management. So what are the elements of a process? We have to know that, yes, we know a process is a program in execution. So basically, suppose if I am playing a game, like let's assume the game I'm playing is FIFA. So FIFA is a process, so it will have a name, that FIFA game. But what are the other elements to actually make sure that a process is learning or process is working properly? Okay, computer actually needs a lot of data about the process. So all of this data is actually represented in operating system in a process control block. We call it PCB, process control block. So all the data about a process, all the information that is needed by operating system is represented by process control block. Now, what are the elements of process control blocks? First of all is the identifier, unique process ID. Each process in our computer have to have a unique process ID so that you can identify the process instantly, and no two processes will have the same ID. Secondly, state. So we will discuss about the state in the upcoming slides. So for now, let's just in short that each process have some different states. A process can be a new process, that is, it just started. It can be a ready process, that means it is already running. It can be halted, and so on. So we'll discuss about different state that a process can be in. And then there's a priority, that the process will have different level of priority. Some process will have a higher priority, some will have a lower priority. This priority also helps us with the interrupt. And then the program counter. So the program counter indicates that to run this process, so let's assume I am playing a game called Dota, okay, or another game is called FIFA. So each of these games are stored in different part of my computer. Okay, so if I want to execute those processes, I have to know that where the instructions or the programs are situated in our computer. So this program counter will indicate the address of those instructions for this process. So each process will have a different instruction because each process is actually stored in a different place of a hardware. Then we have memory pointers, okay, that includes the pointer to the program code and data associated. So all the data and the memory will be available in the process. Then we have the context data. So these informations, these terms might feel a little bit unfamiliar, but don't worry, we will discuss them very soon. So we have context data, we have IO status information, that was input output information. So which information, input output devices are needed for this game or this operation or this process. So let's assume you're actually what can be example. So whenever you are actually like talking to your friend in a Facebook, okay, let's assume you are in the Zoom, okay, or you are in the Facebook, you want to make a phone call to your friend. So what the process will first check, the Facebook will check whether you have a microphone or not. If you want to make a video call, it will make the video, a webcam will also be included. So whenever we are running different processes, we have different input output device requirement. So one example was that headphone, webcam, so on. And then finally the accounting information, the time, the needed, the resources that needed for the process to run, the CPU or the clock amount, and so on. Then we have this process execution trace. So let's discuss trace now. From the slide. So first of all, what is a trace? Okay, so we now know what is a process, that is a programming execution. We know what is the PCB, that the information needed to store for a process. So what is a trace? So first of all, the behavior of an individual process can be characterized by listing the sequence of instructions that execute for that process. So the behavior of the processor can be characterized by the showing the traces of the various processes. So basically, as you can see from the definition, that whenever you are executing a program, okay, trace, the exact meaning of trace in Bangla, if I go for the wordly meaning of, okay, so trace actually means like in mathematics it means to discover, to detect, okay. So in Bangla, the trace, what is the perfect word for trace? Chinno, or like what can be like খুঁজে বের করা. So these are the words in Bangla that we have for the trace. So basically we can say that I am following his trace, I am following his like where he is going, we're doing that. So in a process, okay, so trace is basically the behavior of an individual process, okay, but we can follow the trace by how. So we can actually see that if I want to run this game, what are the instructions that have been executed. So that instructions can be called the trace of that program. This is not the only correct definition. There are actually a bit more complicated definition, but I'm just giving a simple idea about the definition. So a trace can be like a program has been executing or is being executing, and the trace is that so far to execute the program, what changes have been done or what instruction that been executed. So the chinno or the like the track, okay, the steps have already been taken are called trace. And we can actually characterize the behavior of different processors as well. So let's see some examples. So another one is a dispatcher. So what is a dispatcher? It's a small program that switches the processor from one process to another process. So you are actually running a program and suddenly there's an interrupt and you need to run another program. So a dispatcher, what it will do, it will actually help you to switch from one process to another process. So from one program to another program. So let us see this example. So here there are three programs in the figure. As you can see, we'll first go to this one. We have this main memory. In the main memory, these are the addresses. So let me actually zoom it. And so these are the addresses of the computer. Okay, so like addresses of the memory. So we have 0 address, we have 100 address, we have 5,000 address, we have 12,000 address. So these are all the addresses. Okay, it starts from 0. So in the 100 address, okay, the memory location 100, we have the dispatcher program. In memory location 5,000, we have the process A. In memory location 8,000, we have the process B. Memory location 12,000, we have the process C. So these are all the memory location or memory allocation of different processes in a computer memory. Okay. Now, what is a trace? So let's assume you will start running the program A, and after executing up to 11th instruction, you actually interrupt occur, and that interrupt takes you to program B. And you are executing program B, and after executing 3 instructions, another interrupt occur and it takes you to process C. And you are again executing process C one by one, up to your processing 11th instruction, and then another interrupt occurs and you go to another program. So as you can see in the list of trace, what we have the list of all the instructions that have been completed. So basically the trace of A means the instructions of A that have already been completed. Trace of B means the instruction of B. So we can see that in Bangla that what we're saying, like we can see the chinno or the like what is the exact word, like what have we done so far, আমরা এই পর্যন্ত কি কি instruction শেষ করে এসেছি. So we can actually see those here. Same goes for process C. So a trace is basically a list of all the instructions that you have completed so far. So what is the need of trace? Why we actually use this? Okay, and what is the need of dispatcher? So I have already told dispatcher is a program that helps you to switch from one process to another process. So here, this is an example. So first, let us assume I have started with process A. So this is process A we are executing. Okay, the beginning of the program. So we first execute instruction number 5,000, then we execute instruction number 5,001, 5,002, and suddenly when we are instructing 5,005, okay, there is a timeout or maybe there is an interrupt. And when there's an interrupt, that means I have to switch to another process. Okay, so let's assume this is a timeout. That means each process will give maximum of 5 amount of time. And then suddenly I have to use a dispatcher, this dispatcher program that is situated in location of 100. And using the dispatcher, okay, we can actually switch to another process. That is, let's assume this is C. And all this 1, 2, 3, 4, these numbers that you see here, what this number means, these are actually time that you are using the computer and time is going by. So from 1 second to 6 seconds, you are using process A. From 7 to 12, these seconds were wasted or used to actually switch from process A to process C. And then when you're executing process C, okay, suddenly another interrupt request came. Okay, and as to follow the interrupt request, sorry, this will be process B, my bad. This is process B, 8,000. And then an interrupt request came and you switch to process C. And then up to 28, you work with process C. Then again, you go back to using a dispatcher, you go back to process A, and the program goes on like this. So what we actually want to see from here, okay, what is our focus? So we can actually, we're trying to understand that whenever we are working in a computer, okay, we have only one CPU, one processor, okay, and using one processor, how we can execute multiple programs at the same time. Now, here, as you can see, we had 3 different programs. We start with program A, and after certain amount of time, another program that is we call dispatcher, okay, it helps CPU to actually load another program. So it loads program B, and then suddenly an interrupt occurs, and again whenever the interrupt occurs, we have to switch from one process to another process. So again the dispatcher comes. So every time you need to switch from one process to another process, the CPU need to switch from one process to another process, we need this dispatcher. Okay, what it does, it loads all the information it has on one process to the store into the memory, and then loads another one. So that's how dispatcher work. And what is the task of this trace? So now as you can understand that whenever we are actually executing multiple program at the same time, we have to actually keep track that which program is done up to it. So if I go in Bangla for 1 minute, আমরা যখন অনেকগুলি প্রোগ্রাম নিয়ে কাজ করব, আমাদেরকে হচ্ছে খেয়াল রাখতে হবে যে কোন প্রোগ্রামটা আমি কতটুকু করছি। সো ধর আমি হচ্ছে তিনটা প্রোগ্রাম নিয়ে কাজ করতেছি, A, B and C। সো আমার কোনোভাবে আমাকে খেয়াল রাখতে হবে যে এ কতটুকু শেষ হয়েছে, বি কতটুকু করা হয়েছে, সি কতটুকু করা হয়েছে। সো নেক্সট টাইম যখন আমি আবার ফিরে আসব, আমি যেন বুঝতে পারি যে আই হ্যাভ টু স্টার্ট ফ্রম 8004। নাও one solution can be that, sir, we have IR, instruction register, for that actually stores the next instruction to be executed, right? But the problem is IR is only in the CPU. So whenever a program is loaded into the CPU, then it only keep tracks of that program. So whenever we are working with multiple program, we have to keep the track or the trace of all the programs, and that's why the trace comes in. So I hope I made this topic clear, but now I will pause for 1 minute, and if you have any confusion you can ask that, sir, I didn't understand what is process. So the questions we have covered so far: what is a process, what is a process elements. Okay, we have talked about different elements, we have talked about trace, and we talked about dispatcher and how these two work. So up to slide number 7, do you guys have any confusion? So I will pause for 2 minutes. So next topic is process creation. A process may create several new process itself during execution time. So let's assume this is a root program, and whenever computer starts, the root program starts. Let's assume this is like a kernel. So this root program will call 3 other programs or processes, sorry, page daemon, swapper, and init. And this init program process will call different other processes, and it goes on like this. So basically whenever you are running a process, by intention or by unintentionally, many other processes being created. Let's assume you're listening to a music, okay, and you're just using a VLC player, okay, and then suddenly you want to update the VLC player. So another process will be created to do the update function or the update process. You're listening to the VLC player and you want to see the video as well. So the video function will also be called. So what happens whenever we are using one process, by intention or by unintentionally, we actually create many sub processes, okay? So all these processes, they have a name. So the one process is called parent process, another process is called children process. So the process that creates the other process is called the parent. So here, let's look at this diagram. Root is the parent process for page daemon, swapper, and init. Init is the parent process for user 1, user 2, user 3, and it goes on like this. So the process that creates another process is called parent process for that one. So this is just like a human parent theory. So your parent is like your father and mother, and their parents is like your grandfather, and so on. So each process has their creator or the parent process, and it may in turn create other processes, forming a tree of process. So basically from one process you can create other process, those processes can create many more. In this way it can goes on. So whenever we're creating a process, these are some challenges or decisions we have to make. So first of all, let's assume I am a parent and I have like 100 millions of, I have this amount of money, okay, 100 million. So whenever I'm having 100 mil, okay, so first of all, resource sharing. So let's assume my money is my resource. So all of your money is stored in one bank account. So whenever you have a child, you have a decision to make whether you and your child will share all the money. That means you'll share the same account. You can take money from that account, your child can also take money from that account. So that is called parent and children share all the resources. Okay, that you will share your money. Or in case of computer, it can be like resources. Let's assume it can be CPU time, it can be memory address, it can be uh, input output devices, and so on. Second one, children share a subset of parents resources. So basically out of this 100 mil, you take to 10 million, okay, and then you actually let your child use only any money from the 10 million. The rest 90 is reserved for you. You don't let this person, your children, use that 90 million. Third one is parent and child share no resources. So basically you are a parent and you actually don't know that you have to earn your own money, son. You will not get any money from me. This is actually a threat my father used to give me all the time. So that when you grow up, you will not get any money from me. So please try to get a good job. So, and this is the example of resource sharing. So parent and children share all the resources. Parent share subset of parents resources, and parent child share no resources. So these are the decisions that you have to make. And then in terms of execution, okay, so what in terms of whenever a process is executing, parent and children can execute concurrently. That means they're actually different. Okay, there is no relationship between them. Parent goes their own way, child goes their own way. Okay, so they have no relationship between them. Parent doing one thing, child doing another thing. Or it can be like this, that parent wait for the children to terminate. So basically parent will be always there, it will wait for the child. So whenever the child is finished doing its work, only then the parent will be finished. Okay, so the parent will be waiting for the child, or you can say the child will be dependent on the parents, or the child will be overlooked, will be looked, what will be the exact word, I don't remember. Like the parent will be take care of the child. Okay, and finally the address space. So what does address space mean? That is the, like in the computer memory, whenever a new process is created, the child will be located in the same address. So basically, like if you live in a house, so this means that child will live in a same house, okay, as the parents. Okay, or child has a program loaded into it. So basically a child will go to a new house. Okay, so this is all about the address space. The address space explanation is a little bit complicated than the example that I have just given. So we will discuss it later, don't worry. So for now, our main focus is this one, resource sharing. So whenever a process is created, it can share resource, or it will share a subset of the resource, or it will not share any resource. Okay, so that's how the process creation works. And now for the last topic for today. Okay, process creation, why we actually create process. Okay, so new batch job. The process is created, the operating system is provided with a batch job control scheme. On a tape days, when the operating system is prepared to take on a new work, it will read the next sequence of jobs. So in short, okay, whenever operating system need to do something new, okay, we have the first reason, one, for creating a process. Two, interactive logon. Okay, so whenever the user actually turns on a system, okay, so basically whenever you turn on your computer, a processes will be created so display function, the login function, and so on. So basically you didn't give any command, but still whenever you turn on your computer, new processes are being created. Then number three, created by operating system to provide services. So sometimes you're browsing your computer and you're listening to this, you're doing that, okay, you're connecting to the internet. So every time you actually do something, give a command, operating system will create new processes so that it actually may help you, or it make things easier for you. And then spawned by existing process. So basically one program was running, and to finish the task of that program, okay, a new program will be created. So a process can be created by operating system to provide a service. It can be created by an existing process, okay, for different purpose. Okay, it can be created for no reason, just when the user login. okay, to support that, and it can be created for a new work, so totally new work, so you from one game to another game. Okay, so these are the reasons a process is created, and here are the reasons for process termination, but we will see them in the next class. We'll finish our today's class now.